So we were talking yesterday, day before, about taking data and seeing if there was a correlation between the independent and the dependent variables. Okay, we used the correlation coefficient to do that, and then we did hypothesis testing on it to see if it was significant. Okay. Now what 12.2 is about is trying to actually determine the line of best fit, okay, or the line of linear regression is what we usually refer to it as, okay, with the math terms. We can see there that's the same data that we used yesterday. It's the same gross domestic product versus CO2 emissions, and you can see that there is possibly or probably a linear correlation here. We went through yesterday, found the linear correlation factor, just off memory, it was 0.8 something. We did the hypothesis testing. The critical values for hypothesis testing were 2.306, and the test value we found was 5 point something. So we rejected the null hypothesis, which would have then allowed us to accept the alternative that said, yes, the correlation coefficient is significant, okay? So now, once we've done all that stuff, now it's, okay, well, what is the line of regression? What is the line of best fit that we could put in there that would allow us to do something called interpolation and extrapolation, okay? Interpolation would be able to find data values that are inside of what we've already measured, okay? So inside, whatever this x value here is and whatever that x value there is, we could use any x value that's inside there and plug it into our formula, and it would find a predicted y value on the interior of this data. Does that make sense? That's interpolation. Extrapolation is on the outside, okay? Or sometimes you can extrapolate is the word we're looking for there. So we want to be able to determine what is the line of best fit. So when you are in maybe a science class, okay, I don't know how, when you're doing labs, when I was in school, and I haven't done a science lab in quite a few years, but we didn't spend, part of that process was understanding that, I can have error in my decisions, error in my measurements, and all that kind of stuff. So what we would do is say, okay, maybe we're going to choose that coordinate and maybe that coordinate for ordered pair, and we're going to create that line, okay? This one we would call maybe x1, y1, this one x2, y2, and then we would run through the formula y minus y1 equals m times x minus x1 with those two ordered pairs, and we would get the equation of that blue line. And that blue line models the data. There's a series of, 4 points above that blue line. There's 3 points, or it looks like 4 points below it. There's 2 points on it. So it looks like we kind of fit that line into that data. Does that make sense? Okay. What I want to work through today, because you could have chosen those 2 points, but your neighbor might have chosen maybe that one and that one, and developed a completely different equation. Does that make sense? Now, if I pick those two, I just got to put a purple line through here. It's a different equation, but is it much different? Slope's relatively probably the same, right? Y-intercepts are probably a little bit different, but if I go out to here you can see how as we go on to larger and larger x values, the distance between these two is going to diverge. So one is going to maybe be a better estimate than the other. Does that make sense? And then your neighbor could come up with another one. Okay, your other neighbor could come up with a third one. So there's subjectivity there. Okay, and we'd have to have the argument. Okay, well, which one best estimates future data or predicts future data. So what we do is we come up with now. All right, so we put that line in there, okay, which now if we look at that line, right, that is the line of best fit, okay. Putting the lines that I drew a little bit ago, and that one pretty close to the blue one I made, right? Okay. But if we look at the one that Desmos puts in there, and I zoom in on these points, did Desmos use that point that I used? No. Did it use any of the points that I used? No. Okay. Desmos does not use, and this is the linear regression model, is that it doesn't use, generally, I won't say always, but it usually does not use specific points that are on your scatter plot. Okay? And so we're going to talk about what is it actually doing here. Okay? Kind of show you a couple different visuals of what the technology is doing. We're going to do it by hand and then ultimately revert to technology. So the key concept, it says, after determining that a linear correlation between two variables is significant, so after we do the hypothesis testing, the next step is to determine the equation of the line that best models the data. Okay? So the regression line, sometimes called line of regression, line of best fit, all appropriate ways of naming this thing. It says the line that models the relationship between two variables that have a significant linear correlation. So the equation can be used to predict the y value for a given value of x. It says although many lines can be drawn through the set of points, a regression line is determined by specific criteria. Okay. Now this explains it. So I'm going to read this to you, but then kind of walk through the image down here after we read it. Okay. So let's consider a scatter plot. Okay. So we've got the scatter plot similar to the data that we just graphed. Okay. It says for each data point, says D sub I represents the differences between the observed y value and the predicted y value for a given x value on the line. Okay, so we could put many of these black lines through our data. Okay, we could put a lot of them through there. Okay, that we might think represents our scatter plot. Okay, but the distance, okay, that is between a data point in any of those lines, okay, so we'll just use this black line as one of those many lines that we put in here. That distance is referred to as D sub 1 for that first point. This is distance is D sub 2, that's D sub 3. So this is the observed value, and this point right here on the line then would be the predicted y value. Does that make sense? Okay, so this point, you know, if we've got I don't know what kind of number. So whatever that y value there is, that is the observed y value. And this would be, so I'll put y sub 0 and I'll put y sub p. And so for that x value, okay, this y value is the predicted y value for our line, but this y value is actually the one that was observed. Okay? What we are trying to do, so these differences, these distances, are referred to as residuals. Okay? So we come back up here. It says these differences are called residuals and can be positive, negative, or zero. Okay? So this one would be negative because it's below the line. This one's negative. This one's positive. This one's positive. This one's negative. This one's positive. And generally what happens is that you'll have, you know, you might, if it's on the line, it'll be zero. But like I said, that's, I won't say it's rare, but you're probably going to get more points off your line than points that are on your line. But if we were to take all of those values, okay, so this one, like I said, that was negative, negative, positive, positive, negative, positive. If we have a lot of data points, almost about half of them below the line, the other half above the line. We add them together, a lot of them are going to cancel out. Does that make sense? So look at D1, D2, D3, D4. They almost negate each other completely. Okay? D5, and then that one up there at the top right says D sub I. They almost negate each other completely. Does that make sense? So if I were just to strictly add those differences, okay, I'm going to usually get around something close to 0, which is not really beneficial for us. Okay? So it says these differences, like I said, are called residuals. Positive, negative, 0. So when the point is above the line, D sub I is positive, negative below, and 0 when on the line. So of all possible lines that can be drawn through a set of points, the regression line is the line for which the sum of the squares of all residuals is a minimum. Okay? So let's talk about that. If I were to add all these up as they are, negative value, positive, positive, negative, positive. Okay? For all different possible black lines that we could draw through our data, okay, if I left it that way and I just looked at them as positive and negative values, most of them are going to be very close to 0. Okay, it's going to be very difficult to find the one that's that minimum. Okay, so what we do is we square these values, because if I square a negative, what's it become? Positive. Square a positive, what's it become? Positive. So now what it does is it forces all of our values to be positive. If we sum them then, okay, of all the different possible lines that could go through there, we sum them and then choose the line that has that smallest sum. Does that make sense? And what that means then is that that line best fits our data. Okay? That's why sometimes, if you remember back to algebra 1, when you guys talked about lines of linear regression, sometimes you call it a least squares line. You ever heard it called that before? Or the line of least squares? Never heard it? Okay. It's a synonym for line of regression or line of best fit. Okay. That's what this is saying right here. We're going to take the sum of these differences squared. Okay. And we want it to be a minimum, so that's where the word least comes from. Okay. So if we were to just sum all D sub i's, then because some are positive, some are negative, we might get a small sum, yet the fit might not be the best, because many positive D sub i's can counter one large negative D sub I. That's another kind of concept that maybe I've got. If I just draw a kind of haphazard one here, I might have, let's say, like a bunch of points like this that have, dumb. Like those would all have small residuals, okay, that are negative. And that point right there has a large residual that is positive, okay. That line is not the best fit line for that data, because we're now having basically one data point counteract 6 data points. Does that make sense? Okay. So that's why it's another reason why we don't want to look at just the differences and add the differences up, but we want to square them and then look at that sum of a minimum. So give you another visual of this, we can look at, where did I put this? Oh, it's in Schoology. So what we're doing when we talk about least squares, okay, and I think I can move my data values anywhere I want to. So you see when I move my data values, my points, it changes the orange line, Okay, it changes these pink boxes, but what's going on there is that these pink boxes are taking this difference. If I take that difference right there and I square it, okay, that would be that difference times itself, right? Well, that gives an area of a square, does it not? Does that make sense? Okay. So what we're doing when we take the least squares, or the sum of the least squares, is that we want, when we do this, we want that square plus that square, those areas, we want those to be as small as possible. Okay? So this is the line. Any other orange line that I would draw through this data, and then look at these corresponding pink boxes, these squares, and add them together, every other line is going to generate collectively a bigger sum of these areas. Does that make sense? Okay. This is the one that produces the smallest sum of areas. Okay. Just click on these and they give you different data values. Okay. Different structures. Okay. But that's the reason why they call it least squares, because when we square that distance, okay, we get an area here for a square essentially. And we're going to add those areas up. Is everybody kind of on line there with what this is doing? Okay. Yes, the point is, so if I take that distance right there and compare it to this distance, they might counteract each other completely. So what we do is we square this one, and now it's going to give me that area, and then I square this one, and it's going to give me that area, and I'll do that with all of them, and I'll be looking then for the one that has when I sum all those little areas together of those squares, when I sum those together, the one that is the smallest, okay? Because when maybe I draw that line right there. That could be another line of best fit. And I could go through my data and I could look at the squares that are created by that one. Does that make sense? With the data points? But that one might have a sum of areas bigger than this one here. So this one would be better than that one. Does that kind of make sense? So what we're doing here is when we go through this calculation, it's basically saying that, yes, there's an infinite number of lines you can put through your data. This process is going to find the one that creates that sum of areas to be the smallest. Does that make sense? And that's the one that best then fits our data. So regression line of best fit says the line for which the sum of the squares of the residuals is a minimum. Okay. Says in algebra in algebra, use 2 points to determine the equation line y equals mx plus b. In stats, we use every point to determine the equation of the line y equals mx plus b. Does that make sense? So when we first started this, I said, choose these 2 points because I chose those two because it looked like 3 or 4 points were above those two, 3 or 4 points were below those two, but that equation was based off of just 2 points. In stats, we're going to collectively use all the points, so all the points contribute to our equation. Okay. So the equation of the regression line allows you to use the independent variable, which is our explanatory variable x, to make predictions for the dependent variable y, which we call the response variable. Okay. So it says the equation of a regression line for an independent variable x and dependent variable y is the following. It's called y hat is equal to mx plus b. Okay. Y hat equals mx plus b. Now, there's some calculations here that we've got to do that might seem bulky. They're not. When we look at this right here, okay, the slope is n times the sum of x times y minus the sum of x times the sum of y all over n times the sum of x squared minus the sum of x, that quantity squared. Okay. So that's our slope. That's how we find our slope. That's defining the slope. That's using all of our points to contribute to slope. Okay. B, or your y-intercept, is going to be equal to y bar, which we'll talk about what that is here in a moment, minus m times x bar. Okay. So y bar, and this is an extended equation here, which means that there is the equation, but it is also equal to that. And then, so if I compare this first part of this equation, y bar, to the first part of that equation, y bar is then, that's the sum of all my y's divided by how many ordered pairs I have, right? But isn't that, if we analyze that, isn't that the average of your y's? Does that make sense? Add up all my y's, divide by how many I have. So y bar, and the bar symbol is what we've always talked about as an average. Okay, so y bar is the average of your y's. X bar is the average of your x's. Okay, so our equation, okay, is going to use those components. Okay. Yes. We'll use some Excel stuff. We're going to do an example of this by hand, and then we're going to use Desmos or Excel. I don't know. I'll have to do some searching to see what Excel offers in regards to line of regression. But Desmos has a really nice structure. It's possible.